Hi, this is obtained when Si or germanium is doped with a trivalent impurity like Al, B, In, etc. The dopant has one valence electron less than silicon or germanium. Therefore, this atom can form covalent bonds with neighboring three Si atoms but does not have any electron to offer to the fourth Si atom. So the bond between the fourth neighbor and the trivalent atom has a vacancy or hole as shown in the figure. Since the neighboring Si atom in the lattice wants an electron in place of a hole, an electron in the outer orbit of an atom in the neighborhood may jump to fill this vacancy, leaving a vacancy or hole at its own site. Thus, the hole is available for conduction. Note that trivalent for an atom becomes effectively negatively charged when it shares fourth electron with the neighboring Si atom. Therefore, the dopant atom of p-type material can be treated as a core of one negative charge along with its associated hole as shown in the figure. It is obvious that one acceptor atom gives one hole. These holes are in addition to the intrinsically generated holes, while the source of conduction is only intrinsic generation. Thus, for such a material, the holes are the majority carriers and electrons are minority carriers. Therefore, extrinsic semiconductors doped with a trivalent impurity are called p-type semiconductors. For p-type semiconductors, the recombination process will reduce the number of intrinsically generated electrons to Ne. We have for p-type semiconductors, Nh is very greater than Ne. Note that the crystal maintains an overall charge neutrality as the charge of additional charge carriers is just equal and opposite to that of the ionized cores in the lattice. In extrinsic semiconductor, because of the abundance of majority current carriers, minority current carriers produced thermally have more chance of meeting majority carriers and thus getting destroyed or neutralized. Hence, the dopant, by adding a large number of current carriers of one type, which become the majority carriers, indirectly help to reduce the intrinsic concentration of minority carriers. The semiconductor's energy band structure is affected by doping. In the case of extrinsic semiconductors, additional energy states due to donor impurities ED and acceptor impurities EA also exist. In the energy band diagram of n-type Si semiconductor, the donor energy level ED is slightly below the bottom EC of the conduction band, and electrons from this level move into the conduction band with very small supply of energy. At room temperature, most of the donor atoms get ionized, but very few atoms of silicon get ionized. So the conduction band will have most electrons coming from the donor impurities. Similarly, for p-type semiconductor, the acceptor energy level EA is slightly above the top EV of the valence band as shown in the figure. So with a very small supply of energy, an electron from the valence band can jump to the level EA and ionize the acceptor negatively. Alternatively, or at room temperature, most of the acceptor atoms get ionized, leaving holes in the valence band. Thus, at room temperature, the density of holes in the valence band is predominantly due to the impurity in the extrinsic semiconductor. The electron and hole concentration in a semiconductor in thermal equilibrium is given by Ne is into Nh is equal to Ni square.